So we continue. Let me just recall what we've done so far, and mostly yesterday. So we've been discussing the potential random analogues of Mantel's theorem and Turan's theorem, and we also counted triangle free graphs. And we managed to prove these random analogues of Ramsey's and Mantel's theorem in the random graph GNP under the assumption that P exceeds 1 over square root of n times log n. And at the end of yesterday's lecture, I gave an argument why we cannot expect the Mantel's theorem to transfer to the random graph if the density, H density P is below a constant over the square root of n. And I also remarked that the same is true for Ramsey's theorem. However, to show this, you need a more sophisticated argument that we won't have at the time to present here. So there's this gap between 1 over kind of square root of n log n over square root of n, where we don't know whether the theorem is true or not. And this is something that I want to address today. And I will start with kind of stating the right version of the container lemma for triangles. So far, I said this is the weak version. So today I'll start by stating the strong version and discussing it briefly, and then maybe instead of the discussion, I'll just show how you can use the stronger version to get rid of this unnecessary logarithmic factor. So this is the plan for today. So without further ado, let's state a theorem. So it will be a container theorem. For triangle free graphs. And now in its strong version. So we will still want to cover all triangle free graphs with graphs that have few triangles. So the number of such graphs will be small. However, now the containers will be labeled by certain graphs, and this labeling will be done in such a way that we will make sure that the container that contains a given graph, it's labeled by the subgraph of this graph. And you will see how this is useful in applications. So the statement is, again, for every epsilon, there is a positive constant C such that the following holds for all n. So now we claim that there is a family let me denote it by script S of n, which consists of subgraphs of the complete graph, whose number of edges is at most a constant times n to 3/2. So in particular, the number of such graphs is at most n choose 2 choose roughly Cn to 3/2. So the number of them is exponential in Cn 3/2 log n. And therefore, if I label all the containers with these subgraphs, we'll get the same bound as we got before. And we also have two functions. A function g, which, given any triangle free graph on n vertices, returns one of these graphs with small number of edges, and a function f, which, given one of these graphs, returns some graph on n vertices. And these functions have the following two properties. So first of all, if for every triangle-free graph F, well, it's in the domain of G, so we're going to apply G to it. So if we apply G to this graph, we will get a graph with a small number of edges that is moreover a subgraph of F. And we can apply now F to anything in here. So we're going to apply F to G of F, and this will be the container for the graph F.
Contains F or contain.
So F contains G of F, and is contained in F of G of F. So F of G of F is the container for F. And kind of before we knew that the container depends on F, but we know now that it depends on F through this subgraph G of F, which is a small number of edges. And the second property is a property of all the containers. So the second property is that all these graphs that appear on the right have fewer than epsilon n cube triangles. So for all S in Sn, the graph F of S has fewer than epsilon n cubed triangles. So still the number of the family, if I apply F to every element of Sn, then I will get a family of containers for all triangle-free graphs. It will still have the same size as before. I mean, the same upper bound of the size will be valid. However, we have this additional property that the labels for the containers are more explicit. We label them through the subgraphs. And you will see how this is useful in applications. So a comment or a corollary, F of Sn, so the images through F of all the graphs in Sn, there are graphs with few triangles. This is a weak container family. For all the triangle-free graphs. In particular, so the strong version applies the weak version because the size of this family, well, F is a function, so it's at most, so the size of the image is at most the size of the domain, and this is at most n squared, choose Cn 3/2, and this is exponential in Cn 3/2 log n. So this is how log n really appears in the exponent.
So what's the PKN? So what's PKN? The meaning of the definition of the PKN?
It's a subset of Kn. Yes. So I could write alternatively. So these are all the subs. So these are subgraphs of the complete graph on the vertices. Maybe we prefer to denote it like this. Is the statement more or less clear? So it's still kind of unclear why do we need to complicate the statement, because the statement now became more complicated, and so far we've only used it to derive the old statement. So let me argue that the fact that we have this explicit function G, it's helping to make some arguments more efficient. And informally, the reason is when we prove things in the random graphs, we union bounded over all the containers. However, now we know that a container that we will seek for a subgraph of a random graph. So F was always a subgraph of a random graph. must be a subgraph of itself, must be labeled by a subgraph of itself, and therefore, in particular, it must be a subgraph of the random graph GNP. So, since it's a subgraph, we'll gain some additional information. There will be an extra event that this is a subgroup of our random graph GNP, and therefore the union bound will become more efficient. And I'll make it explicit now.
Oh, there is one question from Jun. He asked why if Sn is little than Sn.
Why is Sn?
Is little than Sn.
Because it's a function. So to every element of the set, it assigns every graph, so the image is at most the size of the domain. So the illustration will revisit the first theorem that we proved, or sorry, maybe the second, which is Mantel's theorem in GNP, but now with optimal assumptions. And I'll attribute it to Frankel and Riddle. Even though they stated it for 1 over, so n to the power minus a half plus log 1, I think their argument can be made work to give this statement. And the statement is for every delta, there exists a constant k such that whenever p is at least this large constant divided by root n, and then asymptotically, almost surely, meaning with probability tending to 1 as n tends to infinity, the largest triangle-free subgraph of GNP is no bigger than the p proportion of it in Kn plus n error term. So this could be thought of as just little o of n squared p. So this is roughly half of n choose 2p plus little o of n squared p, and we already showed a lower bound which matches it up to this error term here. Okay, so let's prove it, and the difference from what we've done before is that we just remove this log factor, which is turns out to be unnecessary. And this is best possible after the value of this constant, because we had an argument that if this constant is too small, then the statement is not true. Now let m be this number. So it's the extremal number plus delta n squared times p. And we want to rule out G and P having a triangle-free subgraph with n or more edges. And now we'll still use kind of similar approach, so we'll use the supersaturation theorem. Supersaturation, it gives us an epsilon, which depends on delta. So this the supersaturation theorem says that any dense graph with this many edges where I place delta with delta over 2 must have at least epsilon n cubed triangles. Or in positive, if a graph will have fewer than epsilon n cubed triangles, it will have fewer than this plus delta over 2 n squared edges. And now we feed this epsilon to this theorem. So the strong container theorem for triangle-free graphs gives first the constant C, the family Sn, and the functions f and g as in the theorem. And in particular, for every S in the set Sn, f of S, it has fewer than epsilon n cubed triangles, and via the supersaturation theorem, it's a graph whose number of edges is smaller than this plus delta n squared over 2. Because I chose this epsilon to be epsilon for delta over 2 not delta. And now, if G and P would contain some graph F, which is triangle 3 and has n edges, then, well, this is a triangle 3 graph, so let's use condition 1. So then we know that G of F sits inside F, and F sits inside F of G of F. So in particular, G of F is also a subgraph of G and P. And when we intersect G and P with the graph F of G of F, then this contains at least F. F has m edges, so the number of edges in this graph is at least m. And well, we don't know what F is, but now this event that we wrote here doesn't depend on F itself, but only depends on G of F, right? So, and the important thing is that we wrote some event that now depends only on G of F. So if we violate the conclusion of the theorem, then there must be some G of F, which is a member of Sn, so that these two things hold. So in conclusion, the probability that G and P contains a triangle 3 graph which is too large can be bounded from above by the probability that for some S in Sn, we have the following two events. S is contained in G and P, and the number of edges in the intersection of G and P with F of S is at least F. And now we can use the union bound. We can sum over all S in Sn the probability that S is a subset of the random graph, and the number of edges here is at least n. I left some space here deliberately because, unfortunately, so this event is increasing in G and P, and this event is also increasing, and somehow bounding the probability of the intersection of two increasing events. I mean, if one of them was increasing, the other was decreasing, I could use Paris inequality, but I cannot. So let's try to make these events independent. So therefore, let's here only look at the intersection with f of s minus s. So now they will depend on disjoint sets of pairs. But maybe, well, actually, we do know that G and P contains all of S under this event, but Of course, if I remove it, then I lost at most all the edges in S, so this is still true. But now this is the advantage that these two events are independent because they depend on the intersection of GNP with two disjoint sets of edges in the complete graph. So this is in fact now equal to the sum over all S in Sn, the probability that S is a subgraph of GNP times the probability that the number of edges of GNP in the subgraph f of S minus S is at least n minus the number of edges of S. Now, this is of course just P to the power number of edges of S. And let's look here. The number of edges in here is still, well, at most the number of edges in f of S, which we assumed is that, whereas that is at least this minus what's the number of edges of S? Well, it's at most constant times n to 3 halves. Now, we're allowed to choose the constant k as large as we want. And if we choose the constant k as large as we want, then this delta n squared p will completely swallow Cn 3 halves. So in particular, if k is larger than some function of c and delta, then this will be still significantly more than the p proportion of that, so we'll be able to use Hofding's inequality. So this is at most the sum over all S in Sn, p to the number of edges of S, times now the probability that a binomial random variable with this many trials and success probability p is at least its expectation plus, let's say, delta n squared p over 4. So we do know that the probability of this is at most exponential in some constant depending on delta n squared p, where c delta is a positive constant that depends only on delta. And now we're done modulo some a simple estimate. And sorry for the anticlimactic moment, because now I have to erase the full board. Note that this last expression depends on S only through E of S. So let's partition the sum according to the number of edges of S. So this is at most the sum over all possible values for the number of edges of S, which is between 0 and a constant C times n to 3 halves. And we have P to the S times something which is exponential in C delta n squared P. Now, how many graphs are there with S edges? Well, at most, n choose 2, choose S. So this is the sum s from 0 to constant n to 3/2. Now let's bound the binomial coefficient again. Using the inequality A choose B is at most EA over B to the B. So this is at most E n choose 2 divided by S to the S, but we also have the P to the S, which we can add here, and still this exponential term. Now, the nice thing about this function, which takes S to E and n choose 2P over S to the S, that this function it's increasing on the interval 0 to n choose 2P. So this I will leave as an exercise, which means that we can replace or we can bound each of the terms by the term with the largest S. However, also since we assume that P is at least K n2 minus a half, then this means that P n choose 2 is significantly larger than a constant times n to 3/2. So I could also say that whenever I choose a constant gamma, if K is larger than some constant depending on gamma and C, sorry, K of gamma and C, then this will hold. Which now means that I can extend the sum from C n to 3/2 to gamma P n choose 2. So this is equals the sum S from 0 to say gamma n choose 2P. And now using the fact that this function is increasing, each of the terms is equals E n choose 2P divided by the largest value in this range, which is gamma n choose 2P to the power gamma n choose 2P. And again, we have this exponential. And now these things cancel, and we have something which is exponential in gamma log E over gamma times n choose 2P. And if you take gamma to 0, then this converges to 0. So now, if I take my function gamma to depend on delta, then this constant will be below C delta over 2. And we can conclude that this is in fact exponentially small in C delta n squared P over 2, and this calls it gamma is smaller than some function of delta. And also we need K to be larger than some function of gamma and C. And this completes the proof. So if we gained, maybe to recap, the fact that we were allowed to use this function G allowed us to add this extra factor of P to the union bound. So before, if we didn't have this P to the S, then this thing would be exponential in Cn 3/2 log n. However, the fact that we added this P kind of knocked out this logarithmic factor. The calculation may be slightly more complicated, but also the final result is sharp.
There is still a summation.
Right, but the summation in S is just of length at most, say N squared. And this is exponential in N to 3 halves. Yeah, thanks, John.
So, wait a second. The wing log here compared to the weak version, is it because you can do the calculation slice by slice on these ends?
It's because of this P to the S. If you didn't have the P to the S, then it would still be log. Just if you look at the term with S equals to C N to 3 halves. But the fact that you have this additional event, so this is the event that is saving us, which we didn't have before. Before we only used the fact that the second event, but the first event sort of makes the union bound efficient. And another way to think about this is G and P has roughly N squared P edges. And you know that you're looking for the container span only among its subgraphs. So instead of having like N choose 2 union bound of size N choose 2 choose N to 3 halves, you have a union bound of size N choose 2 P choose N to 3 halves. So you have to consider many fewer subgraphs or many fewer containers. But making it rigorous, it requires you to do this. Okay, so exercise prove the random Ramsey theorem under the same assumptions. So this will be your exercise, or one of the exercises for today. And prove that for every R at least 2, G and P is Ramsey for the triangle in R colors, asymptotically almost surely, as long or as soon as P exceeds some constant that depends only on R times 1 over square root of N, so without the log factor. So this is the idea is similar, but it's a little more complicated. Okay, so maybe this is a good time for a 5-minute break. Now let's do something a bit lighter. I mean, it's really fun to do these computations yourself, but maybe to listen to someone else doing it is less fun. So let's do something slightly simpler, and then we'll come back to something more difficult. Now we proved Mantel's theorem in the random graph under optimal assumptions. Well, in some sense, yes, but in another sense, no, because the original statement of Mantel's theorem tells us something stronger. Not only it gives the largest number of edges of a triangle-free graph, but in fact, it says that the unique largest triangle-free subgraphs of Kn are the complete bipartite graphs. So there's still room for improvement in our theorem. And I'll kind of meet it halfway by at least proving that the all largest triangle-free subgraphs of GMP above this density are at least close to being bipartite. And to kind of move from close to exactly, this is really a lot of work. But the close we can handle in the next 45 minutes. But since I guess all of you have seen a proof of Mantel's theorem and know how to prove that every largest triangle-free subgraph of Kn is the balanced complete bipartite graph. there's a very nice proof of a slightly stronger statement, which is originally proved by Simonovich due to Zoltan Furedi, based on kind of an earlier argument of Erdős, and kind of this is really a proof from the book, so to speak. So let me, it will be my pleasure to present it if you haven't seen it before. So the theorem is the Simonovich stability theorem, which is from 1968, but the proof is due to Zoltan Furedi, and it was published in 2015, but I wouldn't be surprised if he already knew it in high school or when he was in high school, not when I was in high school. So, and it says the following: every triangle, every graph G on n vertices whose number of edges is at least the largest minus some t. This graph can be made bipartite by removing at most p edges. Now, so if you take t to be 0, then you get not only Mantel's theorem, but also description of the extremal results. Because, okay, if it's at least the to-run number, then it can be made bipartite by removing 0 edges, so it's already bipartite. But we also know that this is the largest possible number of edges in a bipartite graph, so we cannot actually be larger than this. And this is kind of a really pretty statement, and you can also use the same argument to generalize this from triangles to K4 to every T. So the same statement is true if you replace 3 by r plus 1 and by r. So here's the proof. Let V be a vertex of degree delta, which we define to be the maximum degree of G. So let's consider V to be some largest degree vertex. Now, what does the graph look like then? Okay, there's the vertex V, and these are its neighbors. So this is the neighborhood of V and G, and let me call it B. And of course, the size of B is delta. And also note that the graph has no edges in the neighborhood because it's triangle free. And the remaining vertices I'll denote by A, and so in particular V is one of the vertices which is not a neighbor of V. So now let B be the neighborhood of V, and A be the vertices which are not in V, so in particular this includes V. Now, the important observation is that every edge in the graph has at least one endpoint in A, well, because B has no edges inside, and moreover, the edges that have both endpoints in A have two endpoints in A. So now, let's consider the sum over all the vertices in A. What do we get when I sum their degrees in G? Well, certainly, we won't get more than the number of vertices times the largest possible value of the degree, which is delta. However, the size of B is delta, so the size of A is n minus delta. So this is delta times n minus delta. But on the other hand, when we sum the degrees in A, we see every edge that looks like this once, and every edge that looks like this, we see twice. So this is equal to twice the number of edges of A plus the number of edges between A and B. But moreover, we already noticed that there are no edges in B. So once E of A plus once E of AB is already all the edges of B. So this is equal to the edges of G plus the edges of A. So the conclusion is that the number of edges in A is at most delta times n minus delta minus the edges of G. However, one of the definitions of the extremal number is the maximum over all k times n minus k. So this is certainly no more than the extremal number minus the number of edges of G. But we assume that the number of edges of G is at least the extremal number minus t. So by our assumptions, most t. So we just proved that the number of edges in here is at most t. So now you remove these edges, and what do you see? You see a bipartite graph between A and B. So that's the proof. Now, we would like to do something similar in the random graph, G and P. So kind of our aim is now to prove that actually above in this range, not only the largest triangle free subgraph of G and P has at most as many edges roughly as by its largest bipartite subgraph, but in fact that needs to be close to a largest bipartite subgraph. And we can do it. I'll show you how to do it using the container lemma, the container theorem for triangles, but we will need now a more precise description of the containers. So we know that the containers are graphs which have fewer than epsilon n cubed triangles, and we used it to deduce that they don't have too many edges, not significantly more than half of all the edges of Ka. And there's some extra information that we will need for those graphs that have few triangles and whose number of edges is close to this maximum barrier, something along the lines of that. And such a statement could be proved directly, and you can ask for the details, but I'm going to take the lazy route and derive it from the removal lemma of Ruja and Samotij, which is also a statement that you might know, and if you haven't seen it before, then kind of I'll be also again happy to be the one who shows it to you for the first time. Okay, so this is the theorem of Ruja and Samotij in 1976. And this is called the triangle removal lemma. And the statement is the following. Basically, if a graph has subcubic number of triangles, then you can remove a subquadratic number of edges to make it triangle free. So for every delta, there exists an epsilon such that any graph, any n-vertex graph, P with fewer than epsilon n cubed triangles can be made triangle free by removing at most delta n squared edges. And a corollary of this is, again, for every delta, there exists a epsilon is such that every n-vertex graph, which has at least exn k3 minus delta n squared over 3 edges, the end fewer than epsilon n cubed triangles is almost bipartite. So can be made bipartite. By removing at most delta n squared edges. And maybe I'll leave the proof of it as an exercise. So you can prove it using these two theorems, but maybe I think it's better if you do it yourself rather than it's not terribly difficult. It's kind of just need to choose the parameters in a wise way. And it's not so important that I put here the 3. I mean, you can. Let's make the life easier and put delta over 100. Because what I really want to focus on is to use this statement to prove a kind of a random version of the Szymonovich-Pure theorem. But before I do so, let me ask you if you have any questions about what happened on the previous two boards. Okay, so if not, then since I guess we're all getting hungry, let's just get it over with. So the theorem will say that for every delta, there exists a k, which depends on your delta, such that whenever we assume that p is k over square root of n, then asymptotically, almost surely, every largest triangle free subgraph of GNP can be made bipartite. By removing most delta n squared p edges. And note that this implies a Mantel's theorem in GNP, because take the largest triangle-free subgraph. So it has delta n squared p edges plus some bipartite subgraph. But using Hovning's inequality, it's not difficult to prove that every largest knows bipartite subgraph of GNP can have significantly more than this times p edges, because the number of edges in every bipartition is concentrated. Yes.
When asked if largest is maximum or maximum.
Every largest maximum. In fact, you could also replace every largest with a stronger or with weaker assumption, every triangle-free subgraph of GNP, which has at least this times p minus some delta n squared p, order delta n squared p over 4n. So not only the largest one, but also the ones which are little o n squared p away from the largest also have the structural property exactly like in this statement, but let me keep the statement simple. Is the statement clear? Excellent. So
Can you explain again why it implied Mantel?
right, why does it imply? So take the largest triangle-free subgraph of GNP. And this theorem says that there must be some bipartition, so that the number of edges here and the number of edges here together is at most delta n squared p. So the number of its edges is essentially determined by how many edges cross it bipartition. But you know that for a given bipartition, the number of edges is a binomial variable of this many trials, where this is A, and success probability P. And of course, this is at most that. So it's dominated by this random variable. But this is really tightly concentrated on this expectation, and there's only 2 to the n bipartition. So you can show that in none of the bipartitions you have significantly more than the expectation. So the proof will start. It's a kind of a mantra how you run these arguments. It's always the same start, but then we diverge in how we continue the argument. So as usual, I will take some small constant, let beta be small. Now I have this statement about dense graphs. So I take my epsilon to be an epsilon from the corollary, but instead of delta, I apply it to the beta. So this epsilon is so that every graph with fewer than the epsilon n cubed triangles, and which is this close to, in the number of edges to the extremal number, is beta n squared close to being bipartite. And we feed it. We will feed this to the strong container theorem for triangle-free graphs. Now, in step 1, I will just make sure that the largest triangle-free subgraph will have its number of edges will be close to what we expect. So I want a lower bound on this. sorry, times P minus beta n squared P. And this you can get from that argument. You just choose the largest bipartition. This is the expected number of edges. This is the deviation. And you can prove that this holds with high probability. So this is by holding. And let me denote it by M. And the main step is step 2. Let me say that if G is T far from bipartite, if it cannot be made bipartite by removing T edges, if it cannot be made bipartite by removing T edges, or its most T edges of the graph would have fewer than T edges. So what are we interested in bounding? We want to bound the probability that G and P contains some graph F for some F which is triangle free, has n edges, but moreover it's delta n squared P far from bipartite. This would be enough. Why would it be enough? So we want to show that this is small. By step 1, we know that the largest triangle free subgraph has at least n edges. Now, if we further know that every triangle free graph with m edges that is contained in G and P is not delta n squared P far from bipartite, then we know that it's delta. We can remove some delta n squared P edges to make it bipartite, and we're done. So just the intersection of the events from step 1 and step 2 gives us the conclusion. So step 1 and 2 give the conclusion. Is that clear? So I'll give you maybe half a minute to process it. First step, the largest is pretty large. And then the second step is every pretty large triangle free subgraph must be close to bipartite. So now I will focus on step 2. So let's apply the strong container lemma for triangles with our choice of epsilon to get C, S, and F and G as before. And now, if G and P does contain F for some body F, for some F which is triangle free with n edges, and F is T far sorry. Maybe also let me denote this by P. Is P bar from bipartite. Then, of course, this F must have its own container, its own label, and then the label has a container. So then there is some S in Sn, well, it's G of F, such that, first of all, this S is contained in G and P, and F is contained in Fs. And we will have to argue a bit differently depending on how many edges. So we know also that this graph is few triangles, but the argument will split now depending on how many edges this graph has. So argue differently. And depending on the number of edges in S. And why do we need to argue differently? Because we would like to use this corollary here. But this corollary only applies if the number of edges in this graph f of s is pretty close to the extremal number. And then we know that this graph needs to be close to bipartite. But I mean, nothing prevents f of s to have n squared over 1,000,000 edges, and we can argue nothing about the structure. But on the other hand, if this is n squared over 1,000,000 edges, it must contain a graph which has n edges, and this should be extremely unlikely because this graph contains a p proportion of edges in a graph which is very close to a complete balanced bipartite. So that's why there are two different arguments depending on whether this is very close to the extremal number or somewhat bounded away. So the first case is, I will call small. And this is when the number of edges of f of s is at most the extremal number minus 2 beta n squared. And in this case, it is unlikely that the intersection of f of s with g and p has at least n edges. Because m is this times p, but with 2 replaced by a 1. So this means we're overshooting the expectation by some beta n squared p. And for any given s, this is exponentially unlikely in n squared p with some constant that depends only on beta. So by Hoffning, the probability of this is at most some exponential in a constant depending on beta n squared. This is because n is at least e of f of s times p plus some beta n squared. And the large, well, at some point we need to use some structural argument because we want to do something structural. The large is in the complementary case where the number of edges is close to the extremal number. And since now this since the number of edges, so we still know that the graph f of s has very few triangles, less than epsilon n cubed, and also it's close to the extremal number of edges. So by the corollary, we know that f of s itself is close to bipartite. So by the corollary, we must find some bipartition which depends only on S. Is such that the number of edges that this graph f of s has inside AS or inside BS is at most 6 beta n squared. And the 6, so it comes from the fact that we had a 3 before, and delta should be, beta should be delta over 2. And how will it kind of now, what will the argument be? Know that our graph f needs to be contained in f of s. But f is t far from bipartite. So in particular, the number of edges of f inside A of s plus the number of edges inside B of s needs to be at least t. But the number of pairs in AS and BS is at most 6 beta n squared. So even the random graph GNP doesn't expect to have significantly more than 6 beta n squared p edges inside AS and inside BS. But the number of edges that GNP has in here and in here is of course lower bounded by the number of edges that F has in there, because F is a subgraph of GNP. But by the assumption on F, the number of edges that F has there is at least t, but t is delta n squared p, and we will take beta to be much smaller than delta, so this will be kind of much above the expectation. So we chose beta at the very beginning after we are given delta, so we will arrange so that beta is much smaller than delta, and to make this extremely unlikely. So this is the sketch, and now the rest of the argument is to check whether our intuition checks and whether we can carry out all these calculations using Hopkins inequality and a union bound. So this is what I will torture you with now, and I hope that the 10 minutes that we have will be sufficient. But before I do so, I just want to make sure whether kind of the strategy is clear. Okay, so let's do the computation quickly, more precisely, let's partition S into S small and S large. Exactly like in here, so S small are all those S in Sn for which the number of edges in f of S is at most the extremal number minus 2 beta S squared, and S large is its complement in S. So the probability of the event in step 2 that G and P contains a graph F or some F which has n edges, no triangles, and F is T far from bipartite. Well, this F, when we apply G to it, it either falls in here or it falls in here. So let's split the sum in two. The possibility is that S falls into the small range. And then, in particular, S must be contained in G and P. And the number of edges that G and P has in f of S is at least n. Plus, what if it falls into the large set, then we still must be a subgraph of G and P. However, now the thing that will be difficult to violate is that the number of edges that G and P has inside the set AS plus the number of edges that G and P has inside the set BS must be at least T, because this graph is T far from bipartite. So in particular, for this bipartition that is coming from S, it must put inside at least T edges. Now, note that we have two sums here, 1 and 2. And this is exactly what we've done in the previous case, because M is just slightly above the expectation for this. So this is exactly as in Mantel. And this we will do similarly. So I focus now only on 2. But let me move here. So for 2, and for S in this S large, and let's by excess denote all the edges of Fs inside the set AS and the edges of the graph Fs inside of BS. So this is some subgraph of Kn, but has the number of edges in this XS we said is at most 6 beta n squared. This is the graph that comes from the corollary from the Ruja semi-ready triangle removal lemma and the stability. And I can rewrite now the sum precisely as each term is the probability that S is in G and P, and the number of edges that G and P has among the pairs in XS, this is at least T. And this is an upper tail event again. And this is again the kind of sum that we've dealt with before. I mean, the only difference now is that actually T is way, way above the expectation. So we don't even have to use Hobley, we could use a simple union bound, but say, just for the sake of being complete, this is at most the probability that S is in G and P. And now the number of edges that G and P puts in XS without S, well, it's still at least T minus the number of edges of S. Now these events become independent. So this is in fact equal to P to the number of edges of S times the probability that the number of edges of G and P in this set XS minus S is at least T minus the number of edges of S. This expression is a binomial random variable, success probability P. And here we don't have more edges than in XS itself, so at most 6 beta n squared P. And in here, T was defined to be delta n squared P, and we subtract at most Cn to 3/2. So under the same assumption as before, this is at least say delta over 2 n squared P if K is larger than some constant depends on zero. And delta, and this is exponentially unlikely, and we finish exactly the same as we finished before. And I think maybe once a day is more than enough to see this derivation. So I'll just finish with an exercise, which is the following: prove that if n is at least some k delta n to 3/2, almost all graphs which have n vertices, m edges, and no triangles can be made bipartite by removing at most delta m edges. So we leave the realm of random graphs, and now we're talking about random triangle tree graphs. So what do I mean by this? Draw a triangle tree graph with n vertices and m edges uniformly at random, and prove that a typical such graph is close to bipartite. So if you remember in the first lecture, we talked about the theorem of Erdős, Plattner, and Rothschild. We said that the random graph, if we don't specify m, then it's actually bipartite. And here, if we specify the m, just prove that there's some bipartition that contains 99% of its edges. And let me stop here.